today we are going to start with another concept of semiconductor. So it is the semiconductor currents. So in semiconductors, charges move in two basic ways. They are pushed, called drift, and they are spread, called diffusion. So these two ideas paired with one elegant relation explain so much conduction, injection and devices, and even how we measure carrier density. So today we will derive and see each concept and finish with a practical measurement of Hall effect. So our discussion continues in the direction of drift current, diffusion current, Einstein relation, mass action law, and then finally Hall effect. So to start with, first we are going to discuss with the drift current. So the drift current is defined as the flow of electric current due to the motion of charge carriers under the influence of the external electric field. So whenever an electric field is applied, the holes move in the direction of negative terminal of the battery and the electrons move towards the positive terminal of the battery. This combined effect of movement of charge carrier constitutes the drift current. So as you can see here in this diagram, the electrons are represented by the this negative signs in yellow color, and the holes are represented by the positive signs symbols in red color, and they will move in the direction of towards the negative terminal the holes will move, and towards the positive terminal of the battery the electrons will move. And we already know that the current will move from positive to the negative terminal. That means the holes will follow the current path and the electrons will move in the opposite direction to the current. So now if we determine the drift current density due to the free electrons, it is given by this relation, and the drift current density with respect to the holes is given by the second relation. Now here we have N and P are the number of free electrons per cubic centimeter, and mu n and mu p are the mobility of electrons in centimeter square per whole seconds, and E is the electric field intensity in volt per centimeter, and as we know Q represents the charge of the electron. So this is the drift current that we observe in a semiconductor. Now moving on to the second concept, which is called as the diffusion current. So in diffusion current, it is possible for an electric current to flow in a semiconductor even with the absence of the applied voltage, provided a concentration gradient exists in the material. So in a semiconductor, the charge carriers have a tendency to move from the region of higher concentration to that of a lower concentration of the same type of charge carriers. Thus the movement of charge carrier takes place, resulting in the current called as diffusion current. So as you can consider, as we see here in this diagram, where we have injected holes into a semiconductor, and whenever we are injecting the holes, then it will get accumulated in a particular area, which will have or which will turn into a higher concentration. Now as we know, the concentration gradient is high at this end and it is lower at the remaining end. So what will happen, the holes will move from this higher concentration to the lower concentration, and it will form a structure like this. So this is causing a movement, and that movement is called as the diffusion current, which will create a current which is known as diffusion current. So here, as we can see on the graph, the diffusion current depends on the material of the semiconductor and charge carrier and the concentration gradient. So the diffusion current density due to the holes is given by this relation. Since the hole density decreases with the increasing x, as you can see here, and is shown in this figure, and the value is negative. So Jp has a positive sign in the positive x direction, and diffusion current density due to free electron is given by this relation. And considering the sign convention, so we may write the equation with the presence of a negative sign. So the total current in p-type semiconductor and n-type semiconductors are given by the combination of both drift and diffusion currents. So this is all about the drift and diffusion currents. The next concept, that is the Einstein relationship for semiconductor. So it is a beautiful and crucial result which links diffusion and mobility, and it tells us that diffusion and mobility are not independent. The thermal motion ties them together. So to start with, let us consider from the thermal equilibrium, we have the drift current, total combination of drift and diffusion current be given as equals to 0. So now for electrons we have the diffusion current as q dn dx, and we have the drift current given as mu and e. Now from this equation 1 we can write this as qn mu and e minus of qdn dn dx equals to 0, right? Now we can simplify it like dn dx. Now here q will get cancelled, so we have e equals to dn dx, right? So moving forward, using Boltzmann relation, we have nx equals to n naught e to the power minus q by kt phi dx. Now if we take differentiation, dn dx will be equals to nx the e to the power term will get eliminated. So moving further, the electric field is given by minus of d phi dx. So if we put it here in the equation, so we can write it as nx minus q by kt into minus c, so which will be finally equals to nx q by kt into e. Okay, so now putting these values in this equation, suppose 2, so what we have is, putting these values in equation 2, we are going to have n mu and e equals to dn n q by kt into e. So here e and e gets cancelled, n gets cancelled, so we have mu n given as dn into q by kt. So now if we determine dn by mu n, so which will be nothing but kt by q, right? So similarly, if we determine, this will be equals to dp by mu p. Okay, so which gives rise to the Einstein relation, which is given as dp by mu p equals to dn by mu n equals to kt by q. Now this kt by q is given as Vt, and this is at room temperature of 300 degree Kelvin, and will be given by this relation T by 11600. By putting the value of K and Q, we get this relation T by 11600. So now here, if we put at room temperature, the value of Vt will always be coming as 26 millivolts. So this is the Einstein relationship for the semiconductor. So moving on to the continuity equation. So in device problems, we combine drift and diffusion with generation and recombination through the continuity equation. So also when we device is biased and the electrons and holes get their own quasi-Fermi levels, so it is useful for later device analysis. So the continuity equation is given by this relation. So this is for holes and this is for the electrons. So now moving forward, next topic is our effective mass and mass action law. So when externally applied electric field in a crystal is very much weaker than the internal periodic field produced by the lattice structure, it is possible to treat the holes and electrons as imaginary classical particles with effective positive masses, which are given by Mn and Mp. So in the perfect crystal, these imaginary particles respond only to the external fields. So here the Mn represents the effective mass of the electron and the Mp represents the effective mass of the holes. So now moving into the mass action law. So mass action law is an equilibrium relation where the product of the electron and the hole densities is equal to the square of the intrinsic condition. So here N and P represents the product of electron and hole densities and Ni represents the intrinsic concentration. So Np equals to Ni square represents the mass action law, which is also known as law of electrical neutrality. So now if we consider a value of suppose Ni given as 1 into 10 to the power 10 centimeter cube inverse centimeter cube, and we dope suppose with the semiconductor with electrons of 1 into 10 to the power 16 centimeter cube inverse, then the number of holes will be equals to Ni square divided by n. As we know, n into p equals to Ni square. So by putting the values, so Ni square is 1 into 10 to the power 10 whole square divided by n. The value of n is 1 into 10 to the power 16, which will be coming out as 1 into 10 to the power 4 centimeter inverse cube. So this represents the holes. So now holes are extremely in minority here because we have doped the semiconductor, the intrinsic semiconductor with electrons. So this is one example is shown where we can determine the concentration of the holes or electron depending on the values using the mass action law. The last topic, that is the Hall effect, so which is used for measurement and derivations of the carrier types. So Hall effect is a direct and practical method to measure the carrier types, that is whether we are having N or P type material, along with the density and the mobility. So it is a must for labs and short device tests. So Hall effect states that when a transverse magnetic field B is applied to a specimen considering thin strip of metal or semiconductor carrying current I, and electrical field is induced in a direction of perpendicular to both current and magnetic field. So this phenomenon is called as the Hall effect. So as shown in this figure, the I is in the positive x direction and B is in the positive z direction, and the force will be exerted in the negative y direction on the current carriers. That means it will be moving in this direction from 2 to 1. So if the semiconductor is of n type, current is carried by the electron and electron will be forced downward towards side 1, and this becomes negatively charged with respect to side 2, and vice versa if we have it for the holes. So here the potential VH, called as the Hall voltage, is given by this equation where RH is the Hall coefficient And along with that, we can also determine the conductivity and the mobility, which is given by this relation. So for p type, we have mu n equals to sigma n RH, and for p type, we are having the same relation but with respect to the holes. Now, to move forward, let us consider an example and see how we can use this Hall effect for determining the solution to any question. So suppose the current I is given by 10 milliampere, so which is 1 into 10 to the minus 2 ampere. So and the B value is given as 0.5 and D is 0.5 and measured VH is 0.5 millivolts. So we have to solve for n, where n is given by this relation. So let us consider so now what we have here is B into I is given as 0.5. So let me see the question from here. So V is 0.5, then I is 1 into 10 to the power minus 2. So this is coming as 5 into 10 to the power minus 3. And similarly we have QTVH, which is Q value is 1.602 into 10 to the power minus 19. Then value of T is 5 into 10 to the power minus 4. And the value of VH is 0.5 into 10 to the power minus 3. So after computing, we will get it as 4.005 into 10 to the power minus 26. So now the value of n is given as the ratio of these two, so which is 5 into 10 to the power minus 3 divided by 4.005 into 10 to the power minus 26, which will be coming out as 1.25 into 10 to the power 17. So this is the answer. So thus we can use Hall effect for solving this type of numericals. So along with that, there are various applications of Hall effect, so which are to determine whether a semiconductor is p type or n type, then to determine the carrier concentration, and third will be the measurement of conductivity of a material and then compute the mobility. Then fourth one will be measuring magnetic flux density, because of Hall voltage for a given current is proportional to the magnetic flux. And the fifth one will be we can measure the power in an electromagnetic wave. So these are various examples of or applications of using the Hall effect. So this is what we have discussed today. So what we have discussed all together is like about the currents in a semiconductor. So where drift is the push and electric drive carriers with an average drift velocity Vd equals to mu e, producing a familiar current J equals to Q and mu e, where diffusion is spread, carrier move from higher density to the lower density, producing a diffusion current given by relation J equals to minus Q dn dx, and the elegant Einstein relation, which links the two seemingly unrelated coefficient d and mu, which is kT by q, that small value of 26 millivolts K at room temperature ties thermal motion to the electrical mobility. So in equilibrium, the number of electrons and holes are not independent, which we have seen in case of the mass action law. And finally the Hall effect, where our practical Peter, that is they put the current through an applied magnetic field to measure the transverse Hall voltage, and from pH we extract the carrier density and even the sign of the charge carriers. So these concepts are the backbone of device physics and essential for understanding the diodes. So Like this, there are some common misconceptions and some questions that we have designed in this session. So as we can see here, so we can find out what is the relation between RMS and Fick. So which one we are going to use here. Then Einstein relation holds non-degenerative semiconductors where the Boltzmann approximation applies. Then in mass action law is valid in thermal equilibrium only. Injection or heavy degeneration modifies it. And Hall coefficient signs tells you the carrier charge sign. So one question could be, so you can try to find out the answer and write it in the comments. So which of these would change if we raise the temperature? So that is D, mu or Ni, or everything changes. Then you can try and practice this problem to calculate D from mu using Einstein relationship, where mu is given by these values, and compute the value of P for n-type doping considering these values, and then estimate and from Hall measurement example. So these are few questions which you can try, and you can discuss those depending on your comments, and then if required we will be continuing those in our next lecture. So thank you for listening. Keep joining our classes.